So the question I want you to have in your mind when we're going through this is, how can you be confident that your software has no unintended functionality anywhere in the system? That there is no wings fall off function that is lurking somewhere in the code, waiting to be called by accident at runtime. So we're going to start off talking about some of the basic concepts here. So there are many different types of code coverage and many different code coverage metrics. But before anybody panics, we're going to focus on just 3 of these coverage metrics, and these are the ones that are mentioned explicitly in the DO-178C and related guidance. You can actually trace most of these definitions back to a paper that was published in the mid-90s. It's a joint paper between NASA and the FAA. And this provided a lot of the code coverage definitions and examples that all the later guidance was built on top of. So we're going to be discussing statement coverage, decision coverage, and modified condition decision coverage. First of all, statement coverage, it's fairly straightforward. It's defined simply as demonstrating every statement in the code has been invoked at least once. So here is a rather trivial piece of example code. You can see there are 3 statements there that need to be covered. If you demonstrate you've executed all of those 3, then you would have 100% statement coverage. Moving on to decision coverage, the first thing to note about the definition in DO-178C is that it talks about entry and exits in the program. So the definition given for decision coverage says that every point of entry and exit in the program has been invoked at least once, and every decision in the program has taken all possible outcomes at least once. In the original FAA NASA paper, it does make it clear that it's talking about function entry and exit points. So it doesn't just mean the entry and exit of the entire program. Most embedded systems have a single entry point at boot up and no exit point because they run indefinitely. Instead, this is actually talking about function entry and exit points. So to get decision coverage here, you would have to demonstrate that this decision on the first line here has taken the true outcome, therefore we execute that first return statement, and that it has taken the false outcome, and we've gone through the else branch down there. So moving on, modified condition decision coverage. Again, we're building up the complexity slightly. The definition here, again, it starts with every point of entry and exit in the program has been invoked at least once. It goes on to say every condition in a decision in the program has taken all possible outcomes. So at this point, it's useful to define what we mean by a condition, and that is the atomic Boolean component in an expression. So, for example, in this case, kettle, cup, and coffee are the conditions. So those are things that can't be broken up into smaller parts with Boolean operators in between them. And conditions aren't the same as expressions. So the expression x less than 10 is still one condition because it is a single thing that has a single true or false value associated with it. Point 3, every decision in the program has to be shown to take all possible outcomes at least once, so that's the same as it was before. And then finally is where MCDC is different to some other coverage definitions. It dictates that each condition in a decision has been shown to independently affect the decision's outcome. What this means is I have to change kettle as a condition from true to false without changing the others and show that that can change the true or false value of the whole decision. So I wanted to compare some of the other metrics that we mentioned on the first slide. Condition decision coverage simply dictates that every condition has been true or false and every decision has been true or false. So in this particular example, in the best case, you only need 2 test vectors for full coverage. So the name modified condition decision coverage really comes from taking condition decision coverage and modifying that definition to add that final clause that says each condition has to be shown to independently affect the outcome. And in the best case, that means we need n+1 test vectors, because we can have the same base test vector, for example, false, 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 and then you can flip each of the conditions to true, or sorry, in this case, it's an and, so the base vector is true, 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 and then you make each of the conditions false in turn with 3 conditions. That gives us a total of 4 vectors in the best case. If anyone has struggled with achieving full MCDC coverage in the past, then be thankful. Things could be worse, because there is something called multiple condition decision coverage, which is simply the complete truth table has to be demonstrated for every decision in the code. So in this case, in every case, the best and worst case, you need 2 to the n test vectors. So for 3 conditions, that's not too bad, but if you had 10 conditions, you've got 2 to the power 10 different tests you'd have to run, whereas with the MCDC, in the best case, you could still get away with 11 tests for 10 conditions. So things could always be worse. Why are we using this middle definition of coverage? So if you think about these 3 definitions, they are sort of ranked in order of how difficult they are to achieve. And even for DALE software, we're only using the middle definition. This is quite a nice analogy of how to think about it. If you think about a light switch that's controlled by 3 independent switches, if you were an electrician and you were wiring this up, you wouldn't go through the full truth table of 8 possible settings. You would go to each switch and you'd turn it on and off, and you would look at the light and check that the light worked. And that's really what's happening with MCDC. You are checking the decision works as expected by flipping each of the things that decision depends on. MCDC does imply decision coverage. So every MCDC decision is also a decision. If you've got 100%, if you've covered that for MCDC, then by definition, you've also got decision coverage. But MCDC doesn't necessarily imply full statement coverage, which is why, as you'll see later on, the guidance asks for that as well. Just when you thought it couldn't get any more complicated, there is also a concept of masking MCDC. So here is an example of where the same variable can occur in more than one condition. If we think back to the definition of MCDC, it says you have to show each condition can independently affect the outcome, which means keeping the other ones the same. But if the same variable in my program is used twice, how on earth is that possible? So here's an example. Let's say you're writing a piece of code to determine whether 1 year is after another year. Thinking through the definition, you say, well, year 1 is after, or one date is after another if the year is greater than 1 year. So that makes sense. Or if the years are the same, then if the month is later. Or if the year and the month are the same, then the day of the month is later. And that's how you might think about this logically. That's certainly how I would describe it verbally, and that translates into this following piece of code. But the problem now is that variables appear in more than one condition. So I can't flip the first condition, which is year 1 greater than year 2, without also changing the value of the second condition on the second line. So this suggests that the way that this has been expressed is uncoverable for MCDC. However, there is a definition of masking MCDC, and the masking interpretation allows more than one condition to change, provided that the other condition is masked off so that it can't have any effect on the outcome of the decision. So, for example, if I change the first condition, then I will be, by definition, changing the second condition. But if the third condition, which is month 1 greater than month 2, is false, then any change to the second condition cannot affect the decision. So it is being masked off, and it is acceptable, therefore, for the second condition to change, because we know that change isn't having any effect. And the rationale behind why masking MCDC is acceptable was set out in a position paper from the Computer Certification Authority software team. It's position paper number 6. And for reference, the alternate interpretation is called unique cause MCDC, where you strictly obey the definition. The other is masking MCDC. You can rearrange the code so that variables only occur once in a decision. That can be done in this example, but that rearranging can be quite difficult for a complex decision, and it also can make the code much harder to read. So it is preferable if you have these sorts of things in your code to be able to report, for your coverage tool to report masking MCDC. So why are we analyzing code coverage? It is, contrary to popular opinion, it is not a measure of the correctness of your code. Just because you have covered 100% of your code doesn't mean that that code is correct. The purpose of code coverage is to establish how well your code has been tested. So measuring code coverage on its own is meaningless without a set of tests that you are exercising the code through and measuring the coverage as a result. So if you are missing a test for a certain piece of code, then that will show up as a piece of as uncovered code. So you can identify where you're missing tests. You can also identify if code doesn't have a test case because it shouldn't be there. Going back to the wings fall off example, anything that's showing up as uncovered may be code that shouldn't be there, functionality that shouldn't exist according to the design of the system. We're now going to move on to what DO-178C says about code coverage, which is actually the real reason we measure code coverage. It's not those two things I told you. The real reason is because DO-178C says that you have to. And this is what it actually says in the guidance. I'm not going to dwell too much on the fine details, but you'll notice there is there's an increasing progression of code coverage metrics required as the design assurance level increases. So for level D, there's nothing in that column. There's no code coverage requirement, although you still have to perform testing, etc. For DAL C, you're required to demonstrate statement coverage. For DAL B, statement coverage plus decision coverage. And for DAL A, you're expected to demonstrate statement decision and modified condition decision MCDC coverage. And here is the reason specified in the DO-178C documents. You need to achieve 100% code. Sorry, this is not the rationale. This is what it says you have to do. You have to achieve 100% coverage according to the metrics of your DAL level. And we'll talk about the difference between test and manual analysis a little bit later on. But the key point is the figure of 100. Nowhere in the document does it say you can get away with 90% or 85%. It has to be 100%. And the coverage should come not from just running the software and poking about, but from tests that have been written from requirements. Likewise, with the functional testing, there is an independence criteria which comes into force with DAL A and B, meaning the people analyzing the coverage have to be different to the people writing the code, which have to be different to the people writing the tests, etc. And here we are talking about, again, the purpose of structural code coverage is to ensure that you've done that requirements-based testing process properly. If all of your code is written from requirements and you test every requirement, then you just should end up with 100% coverage at the end. So you can go one stage further really and think about code coverage as a measure of how well your requirements-based testing processes are working. Even having requirements and requirements-based tests in itself is not a guarantee of correctness. Those requirements have to be correct and those tests have to be correct, which means they have to be reviewed. So if everything has been reviewed to an acceptable standard, then you should be getting 100% code coverage. And once again, DO-178C says nothing about how you're supposed to go about this, only here are the artifacts and here is the evidence that you need to provide at the end of the process. So we're going to talk a little bit about how code coverage, structural coverage analysis fits into the life cycle of a DO-178C project. So first of all, the software verification plan needs to talk about how you're going to measure structural coverage, how you're going to address the structural coverage requirement. For example, the tools and methods that are going to be used. These can, like everything else, it can be changed, but it's painful to do so. It's worth putting the research in up front on that aspect. So part 2, software development. You don't have to be doing any structural coverage at this point, but it's certainly valuable to do so. You can easily write code that is impossible to get MCDC coverage for. Not only can you use the same variable more than once in a condition, use the same variable in more than one condition in a decision, you can also simply write a decision which is logically impossible to flip every variable and flip every condition and show the outcome changes. So by measuring coverage early and checking that your code is at least coverable, even if you haven't got your tests finalized, that's a really valuable thing to avoid surprises and code changes late in the project where such things become very problematic. Likewise, you may not be able to do on-target testing and structural coverage analysis, but you can also measure that on host, and we'll talk about that again a little bit later on. So stage 3, the verification stage, is really where lots of testing will be happening and lots of code coverage will be being measured. You should be expecting to show a nearly complete, if not complete, code coverage report in time for SOI 3. The closer you are to 100%, then obviously the easier things are going to be for you. And then finally, SOI 4 is when you need to submit actual evidence of testing in the form of the code coverage metrics that we've talked about so far. So this is the formal run for score, capture the actual evidence and submit that along with everything else. Having defined the code coverage metrics, there are still some open questions that aren't really clarified in DO-178C itself about exactly how those coverage metrics apply to your source code. So a good example of this is the definition of a decision. The definitions, the requirement is that every decision in your code has to take both outcomes, but the document is less explicit on what is a decision in the first place. So this was clarified in another CAST paper, CAST 10, which defined 2 different definitions. The traditional decision interpretation, which is that a decision is anywhere where the code branches and you have some object code that gets executed in one circumstance and other code or no code gets executed in another case. So for example, every if statement would be a decision under the traditional interpretation. The literal interpretation defines a decision as anything that contains Boolean operators or Boolean variables. And so, for example, an assignment that says, for example, int z is equals a and x and y, that would be considered a decision under the literal interpretation because you've got a bit of code that has 2 possible outcomes according to a logical operation, regardless of whether there's actually a branch in the object and the machine code or not. There is still code here which has different possible outcomes, and it's not just from a mathematical point of view. Obviously, calculations have different possible outcomes, but this is different possible outcomes according to Boolean logic. And whilst the traditional decision interpretation fits within the letter of the law according to DO-178C, the literal interpretation fits better, I think, with the spirit of the requirements. And here's a motivating example to back that up, where we have 2 pieces of code here. And these pieces of code basically do the same thing. The function foo is called if x and y are true and not under any other circumstance. However, the version on the left would not require MCDC coverage under the traditional interpretation. There is only a single there's only a single condition inside that decision. Therefore, you only need to show that Z is true or false for MCDC coverage of the left version. On the right version, you would need 3 test cases to show full MCDC coverage. So despite the fact that the code does the same thing, under the traditional decision, you would get away with fewer test cases. There are other complications in things like C++. There are lots of different ways you can have a decision, because under the literal interpretation, any assignment can be a decision, and there are lots of ways that variables can be assigned. They're implicitly assigned when you call a function. So when you pass arguments, that's effectively an assignment. You can have assignments within a decision, so you can nest decisions. So the fourth example here, there's an assignment inside a decision. The third example, again, a function call is an assignment. Therefore, there is a decision nested inside this outer decision. So it's not always obvious where the decisions are, and you need a good tool in order to be able to be confident that you've covered all of them. There is another concept that comes up, which is accidental coverage, sometimes also called incidental coverage. And this is where you pick up coverage not from a requirements-based test, but from some other code that happens to call a function in your system. If you recall, one of the key objectives of measuring code coverage in the first place is to guard against code that shouldn't be there, that doesn't map to a requirement. Now, if you had 2 modules and one contains coverage, they both contain coverage that doesn't map to a requirement and shouldn't be there, and if it just happens to be that the unintended functionality in module A calls the unintended functionality in module B and vice versa, then running a complete coverage campaign across everything and merging all the data together, you could end up with 100% coverage despite the fact that you've got unintended functionality in those functions. So the answer to that problem is to be very strict about when you're measuring coverage and to only measure the tests for that module. So you want to ignore any coverage that might have been achieved during boot up. You want to ignore any coverage that might have been achieved when running tests for other modules, and just measure the coverage for that module in isolation and then merge those results together. Like I said, I'd come back to this, what to do if you get less than 100%. You may find that there are parts of your code that can't be executed through testing, even though you don't have code that doesn't map to requirement or missing test cases. So not every coverage shortfall necessarily represents one of those 2 defects. And a good example of this is if you have a default label in your switch statement, but you've covered every possible case before that, your static analysis tool is going to be telling you must cover this. You must have a default label, but your coverage tool is saying you haven't covered the default label. So one way to get around this is to by manual analysis, or coverage by analysis, or to justify how the coverage shortfall is acceptable. Source code versus object code coverage is another topic that comes up. You can measure coverage at either level, but the guidance says that these have to be in some way comparable. There is an additional obligation for level A coverage that says if the compiler generates code, if you are measuring coverage at the source level for DAL-A project and the compiler generates additional code that doesn't map directly to the source code, you have to verify that. And the way it's worded says if you are measuring coverage at the source level, you have to do this extra work, which suggests that a solution to that problem is to simply measure coverage at the object level instead. But I'll demonstrate why that's not necessarily the right answer to that problem. So as I mentioned, you still have to somehow, if you have this compilers generating code, then even if you're measuring code at the object level, you still have to somehow verify that that's correct, not just cover it. Coverage is not correctness. You have to verify that generated code. So just measuring code at the object level is not sufficient. There's also the requirement that if you are going to measure coverage at the object level, it has to be equivalent to measure coverage at the source level. And by equivalent, it means the same test cases would be necessary to achieve 100% in both cases. And here's an example of why that could be very problematic in practice. Here's a bit of code that returns 1 if the nth bit in a value is set and 0 otherwise. So here are two functions that implement the same functionality. The first one clearly contains a decision. There's the C ternary operator. This could also be written as an if-then-else statement, but quite clearly here we are checking whether that bit is set and returning 1 or 0, otherwise that is a decision. The second version is just doing a shift and a mask. There's no decision there in the literal or traditional definitions. However, both of these compile to identical object code. So on the right-hand side there, you'll see the object code that comes out of the compiler. So given that the object code is identical, how on earth can you guarantee by just looking at the object code that you have the same set of test cases that will be required for source code coverage, when, as we can see here, clearly we'd have a different set of test cases for func1 than we would for func2, because func1 contains a decision and 2 doesn't. So there's something to think about. Other problems with measuring coverage at the object code level is that the concept of a condition no longer exists. There are no conditions in object code. That's a source code level entity. There is no way to perform MCDC and coverage at the object code level in the general case. However, you could try, the compiler could try and guarantee for you a one-to-one mapping between conditions and branches, and then you could measure the branches in the object code and infer condition coverage. There would be a performance penalty for this, just like there's a performance penalty for instrumenting code. So at the end of the day, it's a trade-off. There are some advantages of object code coverage. You can get as little as 0% instrumentation overheads. You can work on pre-compiled components you don't have the source for. You can use any programming language that compiles to object code, and there's no modification of the build system necessary. Another topic that's very important is on host versus on target coverage analysis. In the DO-178B era, it was common to measure your source code, measure your coverage by testing the code on the host computer. As we move into DO-178C, the emphasis has shifted over towards on-target coverage. The mantra is that you fly what you test, therefore you should test what you fly. Get test as close as possible to the final production system. To do that, you need obviously tooling that can work in an on-target environment. You'll often have limited availability of resources, RAM and ROM, etc. However, flexibility is always key here. If you have a tool that can do both, then that's great. You can start your testing on host and then move those same test vectors on target. If you can do that, then you'll be in a really good position. There are different ways of measuring testing. Again, this is not strictly dictated to you. Automated testing is obviously massively preferred. It's more repeatable. You can quickly make a change to the code and repeat your testing. You may still find manual testing in certain components with GUI or interfaces like that. It's important to talk about qualification of any automation tool. We've sort of been implying so far that you're measuring code coverage with some sort of a tool. You could do it by hand. In the very old days, people would step through instructions in a debugger and tick them off that had been covered. But realistically, these days, you're going to want a code coverage tool that will measure that for you. And that tool requires qualification because you're not independently reviewing its output. Coverage tools usually fall under the TQL5 category in DO-330, which is the least strict, and that's because code coverage tools can't introduce a fault, they can only fail to detect one. So unlike, say, a model autocoder, which can introduce faults, a coverage tool cannot do that. I'm going to talk briefly about what to look for in a coverage tool, and then I'm actually going to, I'll show you one of ours. Automation is key to saving you time and effort. Supporting all of the code coverage constructs, all the different places you're going to put decisions is key. If the tool is unaware that a certain piece of source code is a decision, then it won't measure it, and you will have potentially false positives in your coverage result, which is bad. Being able to test on target is key, especially when DERs are really pushing for this. Being able to do both is even better. As I mentioned, you can start your testing campaign and start your test development early. The key thing for successful on target coverage analysis is low overheads. If you instrument the code, it's going to get bigger. That's almost a given. So the lowest overhead, the better. If your overheads are too high, you have to start splitting your code into pieces and running your tests many times, and that's just going to eat into your testing budget. Merging results from multiple different places. Again, being able to merge low-level tests with high-level tests, very important. It's important that the merging is qualified, so you don't have to review it all. Being able to handle missing coverage is important, as I mentioned. On a real project, you're unlikely to get to 100% through testing alone. There'll always be edge cases. Analysis of the results. You need to be able to quickly drill down to where you are missing coverage and do something about it. You want to be able to trace coverage to test cases. That's key for identifying it and eliminating incidental or accidental coverage. Support for CI tools. You want to be able to run, that goes hand in hand with automation. You want to be able to, if possible, run this every night, for example, and you can identify problems early, save money in the long term. And finally, you're going to need to export the results in a format that your certification authorities will accept. There's no point sending them some proprietary binary file that they don't have a tool to open. It needs to be a simple format, but that contains all the necessary coverage data. Finally, you need it to be flexible licensing. I'm not going to dwell on that point. You can imagine why it's important if you have a distributed team to be able to share licenses and not be waiting to acquire one. And unless you want to review everything that the coverage tool does, and you want a qualification kit, you need to make sure that if you are using instrumentation-based approach, that the instrumenter is qualified. That's not always the case, and you don't want to have to review tens of thousands or hundred thousands of lines of instrumented code. So now we're going to dive in and actually show you a little bit of what you can achieve in practice. So I'm going to attempt to share my screen for you. What I've got here is a coverage report from the open source core flight system from NASA. This came with a set of unit tests, which I've run here, and Rapita provided this overall coverage summary. I asked it for all of the metrics that are required for level A, so that's function, entry, exit, statement coverage, decision coverage, and MCDC. You can see at the top here, the tool is it's demonstrating what was instrumented for. If you are working to DAL B or C, then you can tell Rapita I'm not interested in MCDC, and it won't measure and show that to you. Sometimes it's useful, even if you're working to a lower DAL level, to have an idea of how far you are away from MCDC coverage, and that's just in case your DAL changes in the future and you have to do some additional verification. So make sure you have the ability to do that, and it's not some sort of extra license, or that you're using a coverage tool that only supports up to DAL B. There are some on the market that don't do MCDC. GCOV, as a free coverage tool, for example, doesn't do MCDC. You can drill into this data in a number of different ways. For example, I can see just function coverage, and I can aggregate this at the folder or the file level. I can do that for each individual metric. So here, for example, I have statement coverage. I can aggregate this at function level, sort by the percentage coverage achieved, and if I'm interested in a particular function, I can double click on the location, and that takes me through to the source code. And here is a really intuitive, user-friendly way of viewing this data. Statements covered in green here are covered, and the ones in red are not. And there are some statements here that aren't shaded. That's because these are declarations, not executable code. There are a few other ways that we can drill into this data. We have something which we call a tree map, which shows us a hierarchical representation, again, by file, function, or folder. Each rectangle is colored according to the percentage coverage achieved, and the size of the rectangle is proportional to the number of lines of code in that file, function, or folder. So you can see at a glance here where the coverage holes are and how many lines of code are responsible, and you can click on any of those and drill in to the report and look at that in more detail. We can also look at the code coverage by test case. So we ran a series of unit tests here, and I created a different coverage data set for each of those. We can turn this, we can turn these off and look at them individually. So if I just look at the first one, this is just the coverage that this particular unit test achieved, and we can turn each of these on and see the effect that that has on the overall coverage. We can also flip that around and look at the source code and right click on a particular line of code and say, okay, which tests hit this particular line of code. I can see this line of code was only hit by this test here, which is what you'd expect. If you see other tests for other modules showing up here, then that's telling you you've got a problem with incidental coverage. If you do have coverage shortfalls that don't correspond to missing requirements or unintended functionality, you can justify these. So I can create a new justification, and the tool will prompt me to enter a title and a description. To save you having to type out the same thing every time, you can configure templates. So I can, if this is a default switch label, I can quickly add my template in here. You can add your own custom fields to justifications, and you can also add categories and have these set automatically in your template. So you can quickly add justifications, and the categories and references help you keep track of the process. The justifications also migrate with your source code. So when you have a new baseline of your source code, the justifications will automatically migrate, and the tool will prompt you if it's unsure of how a particular justification could migrate because of code changes. So here you can see the coloring has changed to represent the justification of that. We also have additional information available for MCDC decisions to help understand where coverage might be missing for your decisions. So you can list all the decisions in the code, sort these by the number of conditions. Here's one with, let's say, 3 conditions. It's partially covered. If I click on the title, I get a new page of information where I can see the source code, and I can see each condition, why it's not covered. So here, very quickly, I can see we're missing the case. We've observed condition 1 true, result true. We've never observed condition 1 false with result false. So that's the test that we're missing for full coverage of that MCDC decision. Finally, we can merge coverage between different reports. There's a convenient user interface for merging coverage, and then when you've finished, you can export the data very easily in a variety of different formats, including plain text and HTML, which are very accessible formats to view. You don't need to have the RVS tooling installed. I'm going to hand over to Anthony D'Ambrisi from H55, who's going to talk about how they've run their code coverage campaign using RapiCover. Over to you, Anthony.
Thanks for the handover, Matthew. So hello, everyone. Very happy to be here with you for this webinar. And we will take a few minutes together in order to see how H55 is integrating RapidCover into its global software development and verification environments. In order to do so, I will provide a quick glimpse of what H55 is and what is H55 mission, and then develop in few steps how do we integrate RapidCover by looking at our software development environment, how do we integrate software code coverage, how do we integrate RapidCover, and how do we configure it. So H55. So what we see today is that in the aerospace industry, we are facing a lot of new challenges. These challenges are mainly related to new technology because a lot of major players in the aerospace industry for the good target to reach net zero by 2050. And this could be done by developing a new propulsion system that could be either full electric propulsion system or also hybrid propulsion system. When we look at this and when we look at these challenges, we have very big challenges into integration of new high voltage electric system, and this require a new expertise in the field of aerospace. And mostly into when we talk about certification. When we look at a whole new program globally, there is a small percentage globally of a global budget to actually make the proto fly, but the most of it is to make this prototype commercialized and so certified. And this is where H55 provides its knowledge and provide its product to provide globally a full electric propulsion system that is including propulsion units and energy storage, looking at having the most scalable product for our customers and, of course, a certified solution. When we look at this and we see the track record of H55, so H55 is a spin-off from Solar Impulse that you may have heard of. So breakthrough a lot of record in the frame of autonomous flying. So 2 certified aircraft. Also 1 sports aircraft to do aerobatics, and we also have prototype aircraft developed in H55. When you look at this, so it's mostly 4 fully electric airplanes that flew around 48K kilometers around the world, and which represent 1,600 hours of flights. So that's where H55 is taking its unique skill set and know-how. Also, the first and only organization certified by EASA to develop full electric propulsion, meaning globally H55 owns his own POA and DOA, so production organization approved and design organization approved, and we are talking about around 60 collaborators that are hardly working every day to make electric propulsion happening in the aerospace industry. Looking at our products, so we provide a unique proprietary technology that is looking at energy storage and electric propulsion units. So what H55 is offering is a full electric propulsion system within 2 subsystems, electric propulsion unit, which includes globally motor and motor controller, and also energy storage system, so mostly known as a battery pack. And this it's making a whole electric propulsion system. What makes the big difference is the know-how to integrate both subsystems. With the 4 planes we saw a little bit earlier, that's the real know-how of H55, which is able to integrate both subsystems and not developing independently one system and another. And we are currently integrating both, for example, of our system into an experimental prototype aircraft, and the technology will be certified by end of 2023. So when we look at our software development environment, so in all our products globally, we have a lot of software included in our products with various development assurance levels. And inside our software development environment, we integrate continuous integration, for example, with Jenkins. Of course, code static analysis, so where we look at compliance to coding rules that we could do also with some automatic tools, and code coverage analysis that we perform with Rapita, so that Matthew talked to you in the presentation before. In terms of acceptance tests, we use a test framework called Fitness. You will see a little bit more in the next slides. And we do our tests on a test bench, either interfacing with a physical test bench with physical board, for example, electronic board with its software, so globally making on-target testing, or full target simulation. So the core of our environment is our continuous integration server that can be either autonomous, either accessed by a workstation. And then with this continuous integration server, we can access a lot of and run a lot of tools, either static analysis, as you see, either building the software, either accessing Rapita for code coverage measurements, either interfacing to a test framework that will allow us to run the tests either on a test bench in a simulated environment, either directly on target through the test bench in our product, and is also capable of accessing the programmer debugger probe, for example, to execute directly tests on the target. So in terms of code coverage, so the tool we use is Rapita that Matthew presented you before. So our main purpose is to analyze code coverage using our current software development environment, and also using our current test campaigns or test cases. So Rapita today interfaces with Jenkins, because it has an integrated plugin. It interfaces also with a building environment to build the software. Interfaces also with a programmer debugger, so a probe, and with our test framework. And globally, we are able to do testing, either scheduled testing or event-driven, or of course manual. So how does it work globally, the integration of Rapita in our verification, development and verification environment? So we have either a workstation that can launch Rapita, either a continuous integration server. So the first step is that either the workstation, either Jenkins will trigger a code coverage analysis request. So you name it, this could be manually launched or event-based. For example, if we detect a change in our database, the continuous integration server can automatically launch a certain set of tests, so either full, either non-regression test, for example. And after, so interfaced with Rapikover, the second step will be to build the software with Rapikover instrumentation. So we will interface to a builder that will build the software and that will store it into also our configuration management database, which is SVN. Then we will be able to load the software on target through a direct link with the programmer debugger probe. So Rapikover will load the software on the target. And then start to run the selected test over a test framework environment. So fitness here, it's a test framework that will be able to interpret tests and make them runnable on our test bench that is connected to the physical hardware. When this test will have been run on the target, so the whole environment will dump the target memory, because we will have the whole result inside the memory, the hardware memory of our product, and will provide back, process the data. So to analyze the coverage rate we have depending on the test with the number of tests we have run, and then export all the results to a continuous integration server. As you can see here, this is mentioned optional. So either you can use the capacity of Rapikover to generate directly the data, as Matthew showed in his example. Either you can export also to a continuous integration server for further processing of the data. So in terms of configuration, so we do use Rapikover on target. So that it means that all the tests are executed directly on our target hardware, and we do have automated coverage analysis. So globally, what it means is that the full environment will automatically build the software, load on the target, select the test we want to run, and execute it. Dump the memory in order to access the data, access to the log from Rapikover, and then export to our continuous integration environment. So in case, so if you have limitation on the memory limitation on your target, you can also, for example, define a predefined section in order to be able to dump directly from this section. And what we get at the end, directly integrated into the continuous integration environment, are the results of the coverage. So with a nice plugin to quickly see and evaluate the percentage of coverage we have and identify, for example, the missing coverage, and access directly what are the different issues we have seen during the evaluation of the coverage. And of course, you have the ability also to justify the missing coverage directly with the tool. So this is a quite nice feature in order to always have the visibility on and the status on the code coverage of your software. So Of course, you do not need to run it every minute, but it's very useful when you have, for example, a lot of collaborators working on specific part of the software to automatically assess, for example, every day or every week at a certain time, what is the status of the code coverage. And it all runs automatically. And this means that you can have visibility at every time on your software, even if you have also different teams located at different locations, you name it, inside your company or also around the world.
So first up, I have a question from Harriam, and I think this one will be best posed to you, Matt. The question is, does the instrumentation of the code change based on assurance level?
Yes, it does. So measuring MCDC is more difficult than measuring statement coverage. You have to record the values of each condition inside a decision. And the naive implementation of that is exponential in the amount of memory required according to the number of conditions. Rapita has a proprietary algorithm to compress that data as it's recorded, so we can handle really large MCDC decisions up to, I think we've tested 1,000 conditions in a decision, which is hopefully more than you'll actually encounter in your code. But if you are measuring, if you are a DAL C or DAL B project, then the instrumentation is more lightweight and less intensive on target resources.
Thank you very much. And I'll just follow up one while we're on the Rapita tooling. So John asks, how does the Rapita tool subtract out accidental or incidental structural coverage?
So that involves either placing some markers into the code coverage while you're recording it, or downloading the coverage data and resetting it. So there's two approaches. One is external. You pause the target, or pause your program before you start a particular test, and you just zero any coverage that's been accumulated so far, and then run your tests and get the data. Or you can do it programmatically. So in Rapita, you can specify injection points, and you can inject an API call at the beginning and the end of every test, and we will mark the code coverage as belonging to that test.
Perfect, thank you. So I've got a question from Sarah here that will be best for Anthony from H55, which is, what DAL level are the H55 components?
So for the H55 components, since we are certifying today in CS23, we go up to DAL C levels, and with possibility to go also to upper DAL for other certification perimeter like CS25.
Fantastic. Thanks for clarifying that. And I guess that would kind of tie in with what you were saying, Matt, in your presentation about using a tool that will enable you to up the DAL level in the future without having to rework everything.
Yes, as Andrew mentioned, the different sizes of aircraft have different assignment of DAL level. So selling the same component onto a different aircraft, you may have to verify it to a higher standard.
Makes sense. Thank you. So back to you, Matt. We've got a question from Mitch here, which is, when talking about code not mapping to a requirement, is this a high level or low level requirement?
It can be either. So you can get your coverage from low level tests, unit tests, or from high level system tests. And because they're all coming from requirements, and it's actually one of the most efficient ways to complete your coverage campaign is to do as much as you can from system level tests in terms of coverage, and identify any coverage holes that you have from your system tests, and trace the coverage holes to a low level requirement, write a test for that low level requirement, and merge that data in. Getting 100% coverage from system level tests is very difficult because of the number of error cases you have to cover. Getting 100% coverage from low-level unit tests is simply very time-consuming because you might have to write thousands of tests. So being able to merge those two things together is really efficient in terms of completing your code coverage.
Excellent. Thanks for that comprehensive answer. Another one for Matt. Apologies at my attempt to pronounce your name. Jean, I'm going to go with. Does Rapita allow for object code coverage? What would be the limitations on that case? Looking at future sorry, there's a bit more. Looking at future technologies, would something like ARM ISA be digested by the tool?
So first of all, yes, RappiCover, or rather RappiCover 0, which is the zero misinterpretation version of our RappiCover plugin, does support object code coverage. There are some prerequisites. It works using a branch trace, which is a log of every branch in the machine code, whether that was taken or not taken. And you can get branch traces either from a simulator, if you're running on host, or from certain on-target debug interfaces, such as ETM for ARM devices, or Nexus for PowerPC and Oryx devices. So provided we have the tracing capability, we can generate that branch trace, then we can measure code coverage based on that. The other caveat, as I mentioned earlier, is there are no conditions in object code, so we can't measure MCDC. But we have worked with the ARM instruction set architecture previously, so we have the ability to parse and understand that.
Excellent. Thank you very much. So there was a question asked during Anthony's demo, so I think it's to Anthony. This is from Harriam again. Is the target code instrumented? Are you using the instrumented code in production?
So the code is effectively instrumented, but we are not using the instrumented code in production. So globally, the instrument of the code cannot be put on the executable that is effectively embedded in the final product. And this is how also we have the qualification kit from Rapita globally to ensure that that we can certify the actual code without its instrumentation.
Yeah, just to add to that, in order to meet the TQL5, not introducing bugs, the common approach is to repeat your functional testing. You do it once with instrumentation and once without instrumentation, and you can compare the functional test results to make sure those both match, and then you can claim credit for the coverage that comes from the instrumented code. We do actually have a customer that is flying instrumented code, but they have a radically different certification argument that they're able to prove that the instrumentation has no effect on the functionality of their software. But that's certainly the less common case.
Excellent. That's very good. Okay, so the next one I would like to go to here is from Ariane, which is Matt mentioned that some code is written in a way that code coverage is not possible. Is there a checklist for a software developer to avoid those pitfalls?
Not really. It tends to be either by accident. So for something not to be coverable for MCDC, there is a part of that decision that has no effect. There's a condition in there where either true or false has no effect on the outcome, so it's logically redundant, and that's usually a mistake, and that's one of the reasons MCDC coverage is used. There is no checklist that I can think of, but I would say that the solution to this problem is to start measuring your coverage early. Even if you don't have formal tests, you can write tests without requirements for the purpose of checking your code is at least coverable.
Excellent. So there's not one kind of one source of truth on how to do it, but the earlier you start, the better. Absolutely, that makes sense. A bit of a left field one here that I might be putting you on the spot, Matt, but Mitch asked if you could show a sample of a test case. So I think that's relating to the demo. Is that something you could screen share with us, or is that too?
Yes, I'll let me give that a go.
Great.
So I'm actually screen sharing a remote desktop session to a machine running a VM. So I'm taking a risk here, but this is the actual, this is the test code that comes with the NASA CFS source code, which is open source, as I mentioned. You can check that out and have a look at it. This is an example of a test case that is written in a high-level language like C, for example. So you can write your tests directly in the programming language that you're using. You set up some data, you call a function, you do some checks on the outcome, and this is how there are tools that kind of make this a bit easier. So there are tools such as Google Test, and that's how it works. And you're writing your code essentially in source code. There are some advantages to that, but it can be harder to review. It increases the skill level required in order to write tests, because you have to be a C or C++ programmer and understand low-level aspects of how to initialize the data. In comparison, this is a Rapita test spreadsheet. This is the test, one of the tests from the first webinar in the series 2 weeks ago. And you can see that this is an entirely different philosophy. The Rapita test tool will convert this test into source code, so the end result is the same, but this is, in my opinion at least, much easier to review. You can easily see where the inputs and expected outputs are. Any initialization is really obvious. So this style of high-level test writing, I think, is more suitable for DO-178C environment.
Absolutely, and I guess it's a benefit that because it's written, you can edit it in Excel or an open source spreadsheet editor. You don't need to be utilizing a license at that point in time either.
Yeah, that's kind of fairly unique to Rapita test. There are lots of tools that have a user interface, and you can write your tests in a nice, simple way like I've demonstrated, but they do require proprietary software and license to be in place for that. Makes sense.
Thank you. Okay, 2 more questions, and that'll take us through to 1/4 nicely. So I'm going to ask this one to you, Anthony. I don't know if you can ask or have the knowledge at the top of your mind, but were there any places, I guess, in your software where the coverage was different between your on-host results and your on-target results?
Alors, until now, we do not have completed the full test campaign yet, but until now, we do not have the case where it was different. Okay. But it could happen, I think. Matthew give it a hint in his presentation, I think.
Yeah, so a common way this happens is when you have some really low-level code that is dealing with registers, things like that. It's very difficult to test that code on host, so that's one of the advantages. Typically, that code would, if you had an on-host campaign, that code would either have to be justified or you'd have to do a separate manual process for that. Whereas on target testing, that becomes much easier.
Excellent. And I guess it's good to have clarity, even if they are the same. Good. Okay. And finally, one more for you, Matt, which is a question from Brian. Do you have guidance or safeguards that provide confidence that the instrumented code is actually testing a representative form of the target code, as timing is affected by the instrumentation?
Yes, so the argument, as I mentioned, is to run the functional test with and without instrumentation, and therefore with and without this this extra execution time. And if all of the functional tests give the same result, then that is your confidence that you're testing representative functionality in the source code.